My name is Panat, and I'm here with Peter, Kaito, and Jan for the Building CI/CD for API project. What is CI/CD? CI stands for Continuous Integration. In a complex software project, many developers can be working on different features at the same time, so there's a chance for code to have conflicts. Continuous integration helps developers build, test, and merge code smoothly. CD can refer to continuous delivery or continuous deployment. Continuous delivery means all the changes are automatically tested and uploaded to a repository where it can go through code review. Then the changes are manually deployed to a live production environment. Continuous deployment takes this a step further and automates the deployment so that changes to a cloud app can go live within minutes of the code passing tests and review. The important part about these processes is that they are fully automated and each run generates detailed logs for the team to view. What are some benefits of a CI/CD pipeline? Because the pipeline is fully automated, developers can stay focused on writing code and monitoring the system's behavior, leading to increased productivity. Stakeholders and quality assurance teams have easy access to the latest or any version. Each pipeline run generates logs of changes, tests, and deployments available for inspection at any time. If something goes wrong, rolling back changes is as simple as pressing a button. The faster and more automated the entire process is, the faster it is to incorporate feedback from customers and stakeholders. This translates to having more deployments per day. As you can see, some of the most successful tech companies have very high development frequencies. This is possible in a large part due to their highly sophisticated and automated CI/CD systems. We developed a CI/CD pipeline for Python web APIs. We created a command line interface tool that sets up the entire pipeline and connects all services together. Once you provide it with the required inputs, the tool generates YAML files that contain the workflow template. These template files get sent to GitHub Actions, which configures an automated workflow made up of several jobs. All code changes go through the workflow. The commit is checked out and built in a Docker container, formatted, unit tested, and then deployed to a staging environment. If these jobs pass, then the code is ready to merge, but it needs to be peer reviewed before merging. There's only two manual approval operations in this entire pipeline after you commit your code. The first click is a pull request to the main branch, and the second click is the merge. We designed our pipeline to model the real-world software delivery process, and keeping these manual processes ensure accuracy. Once you click merge, the rest of the pipeline takes over. A GitHub Actions begins the deployment of the application to OpenShift. OpenShift checks if there's a Docker file in the repo. If not, then it looks through the repo, check what programming language it's written in, and what type of application it is. Then it automatically generates a Docker file to build a Docker image. This image gets sent to the staging pod. At the same time, there's an outdated version of the app serving customers on the production environment, so OpenShift will automatically scale the pods, swapping the staging and production environment safely and smoothly. For an average Python web application, this entire automated process takes under 3 minutes, faster than it takes to grab a cup of coffee. It's easy and fast to set up and customize to your needs. How can we evaluate a good CI/CD pipeline? Good pipelines are fast, reliable, and accurate. How quickly can developers get feedback for the correctness of their work? If it's longer than the time it takes to grab a cup of coffee, that's a context switch that adds up to hours of lost productivity. How long does it take to build, test, and deploy a simple commit? If that process takes an hour, then in an average of an 8-hour workday, you can only do about 7 deployments. As we saw earlier, successful companies are deploying changes hundreds to thousands of times per day. Businesses today need rapid changes to support changing requirements and markets. Can the pipeline scale quickly to meet new demands and requirements? If everyone is pushing their code to the pipeline, there might be a long queue waiting for resources to free up. Good pipelines have auto-scaling to support productivity. How quickly can we set up a new pipeline? Today's cloud systems are best utilized when software is written as a collection of microservices. Each microservice requires its own pipeline. To support this, you will want a programmable pipeline setup tool that fits existing workflows and store all of the pipeline configuration and infrastructure as code that can be reviewed, versioned, and rolled back if needed. Reliable pipelines always produce the same output given the same input. To ensure this, you'll want to make sure that each workflow starts in a clean state. Using Docker containers means you can guarantee clean and identical resources for each process. Keeping these components isolated from each other also keeps things reliable. Automation is usually good, but a really good CI/CD pipeline accurately models the real-world software delivery process. We want our pipeline to model and monitor complex workflow so human error is minimized. Even with everything automated, it's still good to have a few manual operations performed by a human. As shown earlier, we put two manual proof of processes as part of our pipeline, the pull request and the merge action. Can complex workflows be monitored for correctness? We want something like a dashboard where we have all the information in one place where we can accurately monitor the status of every job in the workflow. Why do we make this? To answer this question, we investigated the current market for CI/CD pipelines and similar deployment tools. We learned about limitations from products in the same space and drew inspiration from them. Some CI/CD pipelines and platforms like Heroku don't have an on-premise solution, which means the user has to send code onto the provider server. Most of them have subscription plans or credit-based tiers. Jenkins is an automation suite that allows you to build, test, integrate, and deploy software, but it's also very complex with a high learning curve. Teams that use Jenkins typically have one developer whose entire job is to maintain and monitor Jenkins. We came up with a list of requirements that would make our system competitive with other existing products. It should be open source and free to use so that anyone can extend features to meet their requirements. The pipeline should be set up in as little steps as possible. Once it's set up, changes by a developer goes through automated testing and deploys in minutes. We focus our scope to Python applications with a public repository on GitHub and hosted on OpenShift. GitHub Actions supports Node.js, Bash, Python, Java, and many more. Unlike Jenkins, the syntax is easy to grasp and the documentation is good. If cloud access is not an option, then it is also possible to use our system on-premise or self-hosted. GitHub lets you have self-hosted runners for GitHub Actions, and this is included in the on-premise Enterprise Edition. Focusing on these advantages allow us to deliver a minimalist but effective CI/CD pipeline. We also made sure not to go beyond our scope. We're not trying to be a cloud provider like Heroku or DigitalOcean. We assume you have the minimum requirements, which is just a GitHub repo and an OpenShift instance. We transform those advantages into user stories, which we use to shape our development timeline for the project's epic. Now we'll take you through each sprint and discuss how we achieve these goals.
We are developing a CI/CD pipeline, so we need some way to see the pipeline in action. This way, we can learn about the CI/CD process and test that our pipeline is working. In the first sprint, we developed a simple URL shortener web application to test out our pipelines. The URL shortener is a full-stack web application that consists of a front end and a back end. You paste in a link and it generates a shortened link. This web application has an API, so developers and other services can create shortened URLs without needing to visit a page. We decided on our tech stack by looking at the most popular frameworks in open source projects. In doing so, our pipeline has a wider range of target users. The backend is in Flask, and the database uses MongoDB. The frontend is in React, which is the most popular JavaScript frontend framework. For unit testing, the application uses PyTest.
In Sprint 2, we started to work on the code formatting and unit testing jobs of the CI/CD pipeline. With many developers working on the same project, there's a high chance that variations in coding style can end up in the code base. Formatting is a helpful element in continuous integration to ensure consistency in the code. In test-driven development, software requirements are converted to test cases. These unit tests allow developers to quickly get feedback on the correctness of their code. A pull request triggers our continuous integration pipeline. Imagine that you finished working on a code on a feature branch and want to merge it to the main branch. The CI pipeline is triggered as soon as you make the pull request. The code formatter is the first job of our CI pipeline. Initially, we implemented a PEP-A formatter based off of GitHub Marketplace action. When triggered, this job makes a copy of the head of the GitHub repo, formats the code, then pushes the changes automatically. Later in the project, we also added an option to choose which formatter to use. Since these formatters only run once on a particular file, the runtime is reduced on subsequent runs. After the code is formatted, a PyTest job runs unit tests. To achieve a test coverage feature, we made modifications to the existing PyTest action. We added a 90% minimum test coverage, If the code doesn't achieve this 90%, the job will fail and the pipeline will not progress. It will save logs and alert the user by email. Every time this job is ran, the users can immediately see their current coverage and which files achieve what percentage. You can also go back and view the logs for previous runs. Up to this point, we have been triggering deployments manually. So whenever our code completes formatting and unit testing on GitHub Actions, we went to the OpenShift web consoles and pressed build so that it would check out the latest version of the code. In Sprint 3, we automated this process using GitHub Actions, where the branch that completes formatting and unit testing is automatically deployed to OpenShift. GitHub Actions needs the user's credentials to perform these operations, so we need a way to automate creating and updating secrets for the users. Therefore, we also created a proof of concept to update secrets for use in various jobs. After the source branch of the pull request is formatted and unit tested, it is then deployed to a staging environment on OpenShift. This job logs into OpenShift using the secrets. Guys, start with the slide.
I'm also choking. All right. Let's start over.
3, 2, 1. After the source branch of the pull request is formatted and unit tested, it is then deployed to a staging environment on OpenShift. This job logs into OpenShift using the secrets and starts to build an image, pulling code from the specific branch. As the job runs, the OpenShift console outputs logs that are mirrored on GitHub Actions. This way, you minimize context switches and can stay on GitHub after triggering the actions.
Once the staging environment is deployed, the action pauses for 30 minutes. But during this period of time, developers should check out the staging environment on OpenShift and potentially run the integration tests. The duration of this time is easily modified with a one-line fix. After 30 minutes, the staging environment and any related files are automatically deleted to save computational power on OpenShift. This indicates the end of the CI pipeline. The pull request will have check marks from all previous actions, and the developer should get approval to merge. The merge will be manual since it is final check before rolling out the changes to master or the production. In Sprint 3, we created a simple proof of concept to automate creating or updating secrets for OpenShift action using Bash script and Python script. We confirmed that our one-click deployment and development idea was totally feasible.
Once we have the proof of concept, we can work on a more robust tool. In Sprint 4, we rewrote those scripts into a CLI in JavaScript. Inspired by our proof of concept script, we created a pipeline setup CLI tool written in JavaScript. It uses the Eclipse CLI framework, which allows us to quickly add new commands. By using Eclipse, we can release our CLI to multiple platforms like Windows, Linux, macOS, and even platforms with ARM architecture using the same code base. We already have installers for each platform, and users can also build from source by cloning our repo. The core feature of the CLI tool is the two commands, config and setup. The config command is used to configure user information for running the pipeline. We take input from users, such as the repo name, access token, and OpenShift server URL. Since some of the information is sensitive, we encrypt them into GitHub secrets. In Sprint 4, we didn't have enough time to implement the setup command, so it will be covered in later Sprint 5 slides.
To summarize, this is what our CI/CD pipeline looks like. Our CI pipeline, which is triggered by any pull request, formats using PEP8 or Black, unit testing using PyTest, and test deploys in the current branch using OpenShift. After all jobs complete, the developer can then get approval to merge and manually merge the changes to an upstream branch. When the merge happens, GitHub interprets as a push to the master branch and roll out the newest version of the master branch to the production environment on OpenShift.
Up to this point, Kaito had been handwriting the actions workflow files for the pipeline. We added a command to our pipeline setup tool that generates these workflows automatically based on a template and user inputs. This tool was nearly complete, so the last steps for us were to test our tools with other APIs not developed by us and prepare the tool for its initial release. The setup command generates YAML files. Although it only asks the user for choice of code formatter, we generate CI and CD YAML files that include code formatting, PyTest, OpenShift build, and deploy jobs. To recap, run the config command, then the setup command. The user can make a commit and push these workflow files to the master branch, and the pipeline will be ready to go. We tested this tool with a Hello World Flask app, with our URL shortener, and with our mentor James API. Everything works great and is easy and fast to set up. As one of the last steps, we packaged our pipeline setup tool into release binaries targeting Windows, Linux, and Mac operating systems. You can go on GitHub right now and download an installer with everything needed to run the tool. The link to the tools repo is in this project's README.
Let's take a step back and evaluate our pipeline to see if we met all the objectives of speed, reliability, and accuracy. Is it fast to build, test, and deploy it? Yes, it takes less than 2 minutes on GitHub and 50 seconds on OpenShift. How long until we get feedback? Feedback is active and instantaneous. If anything goes wrong during the build test or deployment, GitHub shows a red X and sends you an email instantly. Can it scale quickly to meet demand? Yes. Both GitHub Actions and OpenShift has auto-scaling of Docker pods, so that available resources can increase with demand. How fast to set up a new pipeline? Our CLI tool accelerates the setup of the pipeline, and you can install it in minutes. Do the same inputs provide the same outputs? Yes, because we store our configuration as code. Using the same configuration files will ensure you have the same pipeline and workflows every time. Does each workflow start from a clean state? Yes. Our YAML files configures the Docker files of each job so that all jobs in the workflow start from a clean state. Are components isolated from each other? Yes. All our jobs are self-contained and typically only take in one input and give out one output, like functions. This means that if one job failed, it's likely to not affect another job. Does the pipeline accurately model real software delivery process? Yes. We model the user flow of this pipeline based on our process from Spring 1 before we automated everything. Is human error minimized? Yes. Even though most of the pipeline is automated, to trigger the automation, there are 2 manual steps of approval. If you make a mistake, there's still 2 chances for you or someone to check. Can complex workflows be monitored for correctness? Yes. Even though our application is pretty simple, complex pipelines can be monitored in the intuitive GitHub Actions dashboard.
Our project is not free from limitations. We don't have comprehensive integration testing. After the unit tests pass, we only check if the merged code builds successfully. This is fine for simple APIs like the ones we work with in this project, but for larger projects, more integration testing is necessary. Our app has only been tested with Python web apps. So far, our unit tests are running on PyTest only. We can only target deployments onto OpenShift instances. We can address these limitations in future work. Because the pipeline is extensible and open source, we can add in support for other testing suites for integration testing, limit testing, and API end-to-end testing. The last thing we were looking into during Sprint 5 was adding Selenium testing onto OpenShift. It's definitely possible, but requires more work beyond the semester. We work mainly with Python web apps due to the ease of development. But supporting web apps in Node.js or Ruby is a matter of swapping out workflow files customized to those applications. We let developers provide their own tests for PyTest, since it was the most popular one. We could potentially support other testing frameworks and let developers choose to. We focused our efforts on deploying to OpenShift because it was provided for us for free in this class. Even though OpenShift is a commercial product, it is built on open source projects like Kubernetes and OKD. In fact, all the commands we use to deploy on OpenShift are the same in OKD. In the future work, we could extend the functionality of our pipeline and setup tool by letting the user deploy their applications on Kubernetes and OKD clusters in addition to OpenShift.
In closing, here are some lessons we learned over the course of this challenging and fun project. Lesson 1. Improve by struggling first. We struggled with the deployment to OpenShift, getting everything to work nicely. Working on the URL shortener gave us valuable insights on what parts we could improve and where to automate things. For example, manually triggering the build was a pain point for us, so we created an action that triggers a build automatically. As part of the class, we were given a GitHub repo to develop on, but the access level didn't allow us to manage or view GitHub secrets. So we created the CLI tool to automatically update the secrets using the GitHub API, all without having to open a browser. We actually used this tool frequently during the entire process of the project because OpenShift login tokens expire in a day or two. These features all started with a frustration or problem that we wanted to solve.
Lesson 2, run the important tests first. The first stage of our pipeline takes around 2 minutes, but this can be cut down even more by optimization. We should also have run smoke tests and simple unit tests first to make sure that the application is working before going on to more comprehensive testing.
Lesson 3, if something breaks, check if it's our fault first before checking dependencies. At one point, we spent a lot of time trying to debug why deployment didn't trigger automatically because the secrets weren't being encrypted. We checked which of our dependencies were updated, and we were too quick to blame other projects for breaking our pipeline. But this should rarely be the case. All our workflow jobs start from clean, isolated states. So if something isn't working, it's most likely our own fault. Having instant feedback definitely helps us narrow down where the error was.
And that's our project. We'd like to give special thanks to our mentors at State Street Corporation, Ada and James, our instructors, Oren and Michael, Mela, who contributed to our URL shortener, and our friend Adrian, who gave advice on GitHub Actions.